We've been talking a lot about the technology today, but there's a whole other piece to this, which is how to power it. I know some of us power up on coffee, but now we're going to have Ben Waters, who's the CEO of WiBotic, and CEO and co-founder of WiBotic, a company that develops wireless charging solutions and fleet-wide battery management software for mobile platforms of all shapes and sizes, who's going to put it in the context of Red Bull for robotics. Ben, pleasure to have you here. Take it away.
Thank you very much, Robert.
You can applaud, guys. You're tired, but Red Bull it
there
up.
We go. There we go. I knew we were going in the afternoon, so we figured, throw Red Bull in the title. But I hope my talk today will provide a slightly different perspective on humanoids and some of the evolving challenges associated with, operating humanoids both in pilots as well as moving towards production. And that is on the side of power and charging and batteries. I'd like to start with just a simple story that I think many of you will be able to relate with. All of us, I'm sure, have been in a situation where your cell phone's telling you got 1% battery left and you're walking over and right before you're about to plug it in, it dies. The consequences of that are that it's annoying and you got to wait a few minutes for your phone to charge up. WiBotic has been in the business of charging robotics for going on 10 years now. And for a robot, specifically a mobile robot, a wheeled robot, the consequences are a little bit more severe, right? If a robot doesn't make it back to its charging station, the problem is it's going to be stuck in the middle of the floor. The company might have to shut down their operations for a little while if a person has to get in there. Worst case scenario, that can lead to downtime and added cost, and someone has to push it over, right? Now, I'd like you to think about what the consequences are going to be for a humanoid, right? If a humanoid has 2% battery left and its BMS is not a perfectly great system, and so it says 2%, but a minute later, it's actually down to 0, it's going to collapse, right? And now you've got safety concerns you introduce into the picture, right? So the point being, humanoids add another level of complexity and the consequences get greater if the power is not really well thought through when these things are operating fully autonomously. So I'm going to talk a little bit more about some of those challenges associated with keeping humanoids charged up and allowing them to run continuously. But a little background on myself. I'm the co-founder of WiBotic based in Seattle, Washington. I was formerly an electrical engineer, got a PhD in electrical engineering from the University of Washington, and my research was all about wireless power. So we were exploring all the different possible ways you can do wireless charging, and we started a company in 2015 to commercialize what we felt was the best way to do wireless charging, and we have been fully focused on the robotics market, hence wireless robotics, WiBotic. So getting back to the problem, these icons here kind of represent the 3 major problems that I'm going to touch on in this talk. The first is weight. So with a humanoid, particularly a legged humanoid, when you add mass, you create more power that the robot has to burn to keep that mass balanced. It's analogous to a drone. If you have a drone flying in the air, you might think, oh, we'll just put a bigger battery on and that can make the drone fly further, but that's not true. You put a bigger battery on and now it's just more massive, and now really no matter what you do, unless you get really crazy with aerodynamics, a drone's going to fly for about 30 minutes before it has to come back. Humanoid's kind of the same thing. You put a bigger battery, you put more mass, you just have something heavier, the motors are actuating, they're consuming more power to keep that mass balanced. So your runtime is much more restricted than, for example, a mobile robot that's running on wheels. And I'll get back to runtime in a minute. But weight is one of the challenges. The second challenge is dealing with the frequency of charging the battery, right? If your runtime is limited, let's say you're charging, every couple hours, right? And you're trying to achieve a 24/7 operation. Well, you're going through 8, 10, 12, however many charge cycles a day. Your battery longevity is going to be very limited. You're going to be charging your battery many, many more times a day, And just think about the logistics associated with dealing with this, right? This is a problem that WiBotic deals with in our business every day. We have customers who have 100 robots in one facility, 10 robots across 100 facilities, and it might be 1 year, might be 5 years, but when that time comes where those batteries have to be replaced, it is a logistical nightmare. You have cost in buying new batteries, you're dealing with shipping robots back. A lot of the times the robots aren't designed for the end customer to like easily swap a battery out. So this becomes an extremely costly and an extremely challenging thing to deal with at scale. And mobile robots, I would say, is just getting to this level of scale. Many of our customers have experienced this kind of for the first time, and it's a huge challenge, and they're thinking about how they can either forecast this better or design their architecture in a way where the batteries can really last as long as you expect them to. So going back to humanoids, they're going to be charging more times a day. Batteries are going to have to be replaced sooner, even if you have swapping. That's just a logistical and cost nightmare, especially considering that this is an application where you're talking about hopefully hundreds of thousands, and everyone in the world is going to have a humanoid at some point, right? This problem has to be dealt with. And the third problem kind of goes back to the second one, which is the runtime. And that's what I really wanted to focus on here. Most humanoids, if you look at the data sheets of the different ones that are out there, cite anywhere from 2 to 4 hours. Humanoids that are operating on a mobile base certainly are a lot better and longer, and the debate of legged versus wheeled, we've heard a lot about today, and it's a fascinating debate, but it's also fascinating from this perspective about the power. So this gets back to what I was saying, 2 to 4 hour runtime, many charge cycles throughout the day. Batteries are going to not last as long as people expect. They're going to be running them down, charging them up, lots of challenges associated with this. So what do we do about this? I'm going to get into 3 key areas that can kind of address this problem. But first I wanted to mention, I meant to put on this slide, there's a great YouTube channel called The Cleaner Watt. I'm not associated with it. I just think it's really fascinating. Cleaner Watt. They historically talk about batteries and power and everything for EVs, and they've started doing the same type of analysis for humanoids. So they go into deep detail about batteries, what causes batteries to have issues, the cost associated with these batteries, but also some of the market opportunities for humanoids. So I'd encourage you to check that out. Cleaner Watt. All right, there are 3 primary solutions to this problem that I'll talk about. Plug-in charging or tethered operation, which includes tethered operation or requiring a user to manually plug the humanoid in to charge it. The second is contact-based autonomous charging, right? Many of us in the AMR world have probably seen contact-based charging docks where a robot comes up and mates to a contact or a plug. That's another option. And then you have wireless charging. And I'll highlight a couple different types of wireless charging when we get there. But these are all the possible ways to charge humanoids. The one I didn't include on here, which I suppose I could, is humanoids swapping the batteries of other humanoids, but that starts to get complicated, but I have heard about this one. Okay, plug-in charging, and all these images were created with AI, so you can imagine we had some fun putting prompts in to create these images. These don't represent real-world things yet. Plug-in charging, right? Tethered operation is where a lot of companies are starting. When they're developing a humanoid, it's great for safety. They're still working out bugs. It can fall over, and having a tether there is great. And you don't have to deal with constantly swapping batteries and charging the batteries all the time for testing. But in production, I'm sure many of you have been into a facility where you can just imagine, like, would it actually work to have tethers running everywhere? And I think that's just a challenge. From a tethered standpoint at scale. From a standpoint of requiring the user to plug the humanoid in, this is attractive because you can keep the charger off-board the humanoid, right? Just like your EV car, if you're doing DC fast charging, the bulk of your charger is over there on the ground. And you're plugging something in that's just injecting a bunch of current directly onto the battery, which sounds great for a humanoid, going back to the weight problem. But the problem is now you're assuming you're charging a battery that's already compacted into a pretty tight area as fast as possible. So, and going back to the runtime problem, you're charging that battery very many times throughout the course of the day. And we all know that if you charge fast all the time, your battery doesn't last as long as it does if you charge it slowly. And there's some caveats to that statement. There's new battery technology that is accommodating faster charging, but you know, I don't know that it's the battery technology that every humanoid company is using today. I know that it's being researched, and I know people are looking into it to try to charge this way, but it's a challenge. And either way, you're going to be introducing a lot of heat. There's not a lot of heat for heat to go on a humanoid, so there's just some technical challenges associated with assuming this problem is going to be solved by fast plug-in charging like it has been in your car. You know, most cars have water cooling systems that are cooling the batteries actively if you're doing DC fast charging. Difficult to do that type of stuff really well for a humanoid without not bringing in some of the other consequences that might diminish the opportunity of having the charger off board. So that's plug-in charging. Definitely a solution. I'm just talking through some of the pros and cons of thinking about it that way. Contact-based charging. Contact-based charging for robots has probably been the norm, right? Most companies who built AMRs started with and may still today be using contact-based charging, a charging dock that the robot drives up to. Certainly for WiBotic, having done wireless charging as our core product, we've had a lot of companies reach out to us because their contact-based charging dock had challenges, you know, safety. Certainly there's been some fires in the industry with regards to batteries, you know, and chargers thinking they're docked, but the contact wore out and doesn't make a good connection and can create a big challenge. Contact charging becomes trickier for humanoids as well, because where are your contact points? Are they like shown in this picture in the foot? Are they, you know, in the hands? Are they in the back? Is there going to be a seat for the thing to charge and make contact in? So I think contact charging just becomes more challenging than it has been, and it still has all of the same side effects as AMRs today. But certainly contact charging, autonomous contact-based charging is another way that, you know, you can go. And that brings me to wireless charging, but first, before I talk about WiBotic wireless charging, I'll talk specifically about inductive charging. And there is a difference. The physics of inductive and other types of charging are quite similar, but specifically inductive charging systems that operate at a lower frequency are analogous to an inductive cooktop. And that means that if there's a metal object, could be a screw or a washer or something larger like a metal plate, that is on top of an induction charging system, it will heat up. And for big objects, these systems can detect this, but for small objects, and I'm thinking a lot about objects that are probably commonly sprinkled across the floor of a warehouse or a manufacturing facility, like small washers and screws, become really difficult to detect. And most of these systems have a fairly robust foreign object detection system, but even if it can detect it, it means that it's off. And so now you have a charging solution that isn't going to charge until someone comes and, you know, cleans it off, or maybe the humanoid brushes it off. And worst case scenario, if it doesn't detect it, it's going to heat it up and create a thermal challenge. So inductive charging is attractive. I think wireless charging in general, the positive side of wireless charging for humanoids is you get around to the challenges with having exposed contacts, and you can be pretty flexible with regards to where you put the charging pads. You can put them in the floor, and the humanoid can stand on top and charge up through the feet. You can put it in the torso or the back. And so as a humanoid standing up against a platform, maybe dropping a pallet onto it, it can be close enough to a charging zone there. So you can have these charging zones, and you can opportunistically charge the robot very frequently throughout the day, which becomes really difficult to do with contact because you're going through so many more cycles where those contacts are hitting, and then you just introduce more reliability challenges. So wireless charging is attractive for those reasons. Inductive charging has some of the pitfalls of, heating objects that might commonly be found on top of the charging pads. And that really brings me to why we started WiBotic and what some of the research was that we did in wireless charging that led to the products that we have today. So WiBotic uses a higher frequency for our wireless charging systems, and it's typically referred to as resonant charging. And with resonant systems, you just, from a physics standpoint, don't have this phenomenon of heating foreign objects. And the weight of using a higher frequency for the antennas that receive the wireless power goes down quite a bit. Higher frequency typically in electronics means smaller components, and the consequence is usually more loss and more switching challenges and more complexity, which is definitely true, but I'm proud to say that's why we exist, and we've spent 9 years solving a lot of those challenges, and our systems are commercially available off the shelf today, and we have certifications for all these types of things, and we think that WiBotic resonant charging is a good way for people to go about thinking about wireless charging for humanoids. So I'm going to switch gears a little bit just into kind of how the WiBotic system works, but I'm talking more generally about any type of wireless charging system here. The easiest way to think about it is there are 4 main components. On the left, we have the transmitter box and then the transmitter coil, and those 2 components comprise the docking station. And on the right, we onboard the vehicle, a mobile robot shown here, we have the receiver coil and the onboard charger. And one of the things that we've done at WiBotic is we've made the charging universal. So you can programmatically set the type of battery you have. You can programmatically set the charge rate. So you could have a mobile robot with a 12-volt battery and a mobile robot with a 48-volt battery both share a common charging dock. And there's a lot of programmability you can do in terms of, charge fast during the day, charge slow at night, whatever's needed for the application. These are just a couple examples of some of the different things that we do. You can see on the left we have a software platform that gives you insight into all of the charging zones. Coming back to humanoid applications, it's going to be important for the robot to know, okay, there's a charging zone over there, there's one over there. I know I need to charge, so which one do I go to? So we make all of that data from both the charging infrastructure that's deployed throughout the facility and the onboard charger that's built onto the device, easily accessible through an API that is really built for robotics. We do a lot of ROS, we do a lot of NVIDIA integrations, and we think a lot about how our customers need to be able to do these things quickly and easily from a software integration standpoint. We have different IP ratings for our products, and one of the things that we're most known for with what we do in wireless power is flexibility. We have several centimeters of which, if the robot drives in or the humanoid's interacting with, you don't have to be perfectly aligned for charging to take place at its full rated power level with not a huge hit to the efficiency of the system. So this is just sort of showing a fun image of, what does this mean for a humanoid? Well, this is a situation that a lot of companies are thinking about now, right? In those 3 scenarios that I talked about before, you can do wireless charging, you can do fast plug-in charging, you can do battery swapping, you can do tether. It's going to be very interesting to see how companies approach this to be able to build quickly. Everyone's building as fast as possible. There's a ton of money going into rapid development of these things. And just like the previous speaker said, a lot of things are in demonstration mode now, and companies are thinking about, okay, do I introduce this feature to meet these goals that I need to hit for my demonstration mode activities, or am I putting things in there that I know are going to feed into the next version of this where we're going to have to build 100 or 1,000 or more? So it's a super interesting time for businesses to be thinking about the infrastructure that goes into these things, and we've been excited to be a part of it and think a lot about it and think about how they differ from mobile robots. And the last slide is just, again, talking a little bit about software. I used that example before of if a battery doesn't last as long as you think it does, if you designed a battery into your system that's supposed to last for 5 years, and for whatever reason, maybe it was because the end customer didn't plug the batteries in as well as they were supposed to, maybe it's because the robot was actually using that battery all the way down to 0% and charging up to 100% when they thought it was supposed to do 20 to 80, and that went from 5 years to 3 years, and then this other thing went from 3 years to 1 year. This is a huge challenge. So we really track the entire fleet of batteries because we have constant connectivity to the battery through the onboard charger and constant awareness of the charging dock. So we can know things without knowing anything about what the robot's doing of, all right, it's spending this much time at the dock and this much time away from the dock, and that math just doesn't add up. So we're going to send a flag that the customer can investigate to figure out, is there a better way to think about our operations through a software update or something that's going to really gain us back some of that battery longevity. So I think the infrastructure side of battery management, charging in the context of humanoids has some of the highest consequences, but also some of the highest opportunity for innovation and new technology to really play a key role in helping these things scale and, like all of us here hope, become a very useful tool in the workplace and perhaps in a consumer and other settings down the road. Thanks very much to the A3, and happy to be here. And WiBotic has a booth over at the trade show that will have some demos, and would love to talk with all of you throughout the week. So thank you very much.
Thank you very much, Ben. Do we have any questions about the Red Bull of robotics? Anyone want to jump in here? We got Maddie in the back as well.
One here.
Robert. Thank you.
Yeah.
My old man eyes are wearing out as the day goes on here. So there you go.
Very good. All right, so this is the non-engineer question, so apologies if this is simple. But in an environment where humans are getting much more implants, so think pacemakers, iPhone above 14 affects pacemakers, what's the safety implications for workforces that are in that situation?
Yeah, it's a great question. And before we started WiBotic, my PhD was actually about wireless charging for implanted medical devices. I didn't know anything about running a company when we started the company. So I was naturally thinking about this is an obvious, this is what I've been doing, and maybe we should start a company for implanted medical devices. The reason we did not had nothing to do with safety. It had to do with, we learned, I say my first lesson in business was talking to a few of these medical device companies, and they're like, oh yeah, that's a problem. We really want to solve it. New product development probably takes us anywhere from 15 to 20 years. We're like, oh, well, maybe we should find a different industry. But safety is an important consideration, and there are many standards now going on, since the cell phone wireless charging standards. That work really started in 2007, 2008, and then it took till 2016, 2017 for those to first come into phones, and now it's in every phone, right? So a lot of those standards are looking at this. There's an SAE standard for wireless electric vehicle charging. And one of the challenges, one of the reasons why it's taking so long, now granted that's at a higher power level than kind of what we're talking about here. They're looking at 10 kilowatts, 5 to 10 kilowatts. A lot of what we do at WiBotics in the less than 1 kilowatt power level, 1 to 2 kilowatts. But at those frequencies and at those power levels, there is a concern around, really three things when it comes to human safety. Are you interfering with the body, and are you causing physical harm to the body because you're maybe it's like a microwave, right? You're going to be heating bodily things. The other concern is, are you going to be interfering with devices in the body or around the body? So ultimately, wireless charging, all wireless systems, WiBotic, inductive, any other types of systems, are at a low enough frequency where that effect of heating the body is just a non-issue. You're not up in the frequencies where your body absorbs energy, and like a microwave, you're heating, the body. So that's really not a concern. But at high power levels, the field strength absolutely is a concern for certain devices. Now, there's been a ton of papers, I've read a ton of things that are out there that talk about this, and the FCCs of the world are being extremely conservative, as they should be. You don't want wireless chargers to be in parking spaces, and then someone with a pacemaker goes over there and, their pacemaker, something like that happens to their pacemaker. So yeah, that is something that a lot of people have been looking into. But as a company who has our products certified and has gone through all of the FCC, all these levels have now been defined for industrial and general population use below a kilowatt, and some of the standards that are starting to exist for higher power applications are starting to think about how would you solve some of these problems. So, integrating other sensors in the car to detect if a person's around and have the system shut off, right, if they can't demonstrate that they can meet the limits where you're not going to interfere with someone's device. So it's a good question, and it's a topic of a lot of work for really high power EV charging at much lower frequencies. But for the stuff that we do at WiBotic and the certifications that our product had, we've had to go through all that. It's basically held to the same level of safety standards as a cell phone is, which makes it quite difficult because we're operating at a lot more power than a cell phone, but those are the levels of emissions that we have to meet.
What other questions do we have here? Again, we've got Maddie in the back with a mic, if I'm not getting back there. You find somebody, Maddie? There we go.
Yes.
Good afternoon, Pete Hanisch with General Motors. Does your systems by any chance provide any diagnostics or some kind of trending on the battery itself, the health? Because obviously with us, we're very fearful of thermal events, right? Off-gassing, fires, you can imagine. So
Yeah.
if you see anything with your charging that says, hey, this isn't charging at the rate we expect, or we just got to shut down the battery to stop the charge?
Yeah, it's a great question, and the short answer is yes. I sort of say half our business is wireless charging hardware, and half our business is, analyzing all the different types of batteries that we charged over the years and figuring out what insights can we learn over time and really help the battery. Because when we first started, there were so many issues, particularly with drones around, battery management systems. The state of charge estimation would drift over time, and the drone would think it has 20% when it's got 2, and it's going to fall out of the sky. Right? So there were so many challenges like this that we saw, and at the end of the day, we do not make the battery management system. We make the charger, and it's our assumption that the battery has some type of internal protection circuitry. But what we've learned is that different batteries have, some are really good, some are not so good. So, if there's other or even redundant insights we can provide just from how we're looking at things from a charging perspective, that has been very attractive to a lot of our customers. So typically we see the voltage, and typically we know the current that's going into the battery. And yes, we track every historical charge cycle. And one of the things that's super interesting that we notice is most of the time, like when a robot's actually deployed in a production environment, like it's fairly routine. It's not perfectly routine, but it's fairly routine. So we check the voltage that it typically comes into the charger with, and voltage isn't a perfect estimator for how well your battery's doing. It can drift with temperature and other things, but typically we start with the voltage. We know how much watt hourage, amp hourage we put into a battery on a given charge cycle, and you pretty quickly, even after like a month, will start to notice trends. And you'll notice if there's a battery that's not taking as much charge. You'll notice if there's a robot that just has bad charging habits for whatever reason. It's always stuck in that corner, and they don't, it doesn't dock as well with that charger that's over there, so they're charging at a slower rate or whatever it might be. So there is, yes, a lot of insight that we look into with that, and we make that data available both through our onboard charger, so the robot can interpret that, as well as through our transmitter, so that we can talk up into an existing fleet management system and have an alerting system that can inform the end user.
Probably could take one more question here. You're the winner. No pressure.
You had mentioned about 2 to 4 hour runtime on the humanoid batteries. So what would be the average cycle time for recharging those?
Yeah, great question, and really the answer is it depends on what charging approach you're taking. Certainly, it's possible to charge lithium batteries at a rate of, twice their capacity, or maybe even 3 or 4 times their capacity, right? So if you're charging at a rate of 2 times a battery's capacity, that means you're getting, let's say, roughly to an 80% charge level in about 30 minutes. And then that, just like EVs, that 80 to 100 is going to take longer. But you're putting a lot of power into that battery, so your charger and your robot needs to be able to handle that. From an infrastructure standpoint, a lot more high-power chargers. That building's got to have a lot of power if you've got a lot of these things. And then the robot's got to be able to, dissipate that heat that's caused by charging quickly. But in that scenario, you could theoretically operate a humanoid for 2 hours, charge it, let's say, up to 80% in 30 minutes, and then operate again for 2 hours, charge for 30 minutes, and keep going throughout the day. But you're going to be going through 8, ish, or let's see, 2 times, you can do the math depending on the use cases, but if you're going through 5 to 10 charge cycles a day, most batteries, if you look at a lithium battery from a manufacturer, it will say 1,000 charge cycles before that battery starts to reach like 80% of its original capacity. I'm making some assumptions here. There's some batteries that are built to last longer. There's some batteries that, if you don't treat them well, will last way under that. So you can kind of use roughly 1,000 charge cycles. So 5 to 10 charge cycles a day into 1,000. I mean, you're going through batteries, a couple times a year. So that's where all of this stuff becomes really important to think about, and not just from the standpoint of how can I keep this robot up and running all day, but what's it going to cost me and my customer to keep it running, after the battery needs to be replaced.
All right. Ben Waters, WiBotic, thank you very much for joining us here.